All right, I'm very excited about today because we're talking about mean and standard deviation, and this is just such like the heart of the beginning of statistics, and it's just really great. So, first off, let's start with something that you guys know, and you know how to do this very well. You guys know that the mean is the average. And what that means is that you add up all the numbers, or it's the summation of all the numbers. I'm going to use some Greek letters here. So summation, this just means add up all your values, and then you divide them by the number of terms. So add up all numbers, divide by how many? The other thing that I'm going to show you guys here is that when I do the mean, you also could see this a lot of times. We see this in stats as X bar. So that's going to be an important one to remember because when I use my graphing calculator or any sort of standardized calculator to calculate these things, it can give me this X bar, and this is what it's calling mean. My next term right here is standard deviation. Standard deviation is how much on average the numbers deviate from the mean. So how much on average our numbers differ from the mean. So in that exploration that you guys did earlier, you noticed that one of the classes, all the scores were very close together, and the other class, the scores were very far apart. So that first class would have a lot smaller standard deviation because it was more consistent, whereas that second group would have a lot larger standard deviation because they were way less consistent with their scores. Another word that we see sometimes when we're talking about standard deviation is variance, or like how much do the values vary. When we also see this in stats, we usually see this as this Greek letter sigma that represents standard deviation. And it's kind of a funky letter right here, but what it really is it's just kind of like an O or a circle, and it has a little tail. So let's look at some examples right here. Oh, also guys, back to standard deviation, you really want, the standard deviation is how much on average it varies from the mean, and we really want about 70% of that data in plus or minus 1 standard deviation. And we'll talk more about what that means in a second. The following data represents the amount of time in minutes spent studying for a math test for 10 students. So I know my sample size, or my N, is 10. And so our first step is to find the mean, and what does the mean represent in this context? So when I'm finding the mean here, I'm going to add up all these numbers. So add up all them. And I'm dividing that by 10. And when I do that, I get that my mean is 42. What the mean represents in this context is, on average, a student spends 42 minutes studying for math test. All right, so let's get some colors going here. I do know that that's my average value, so I'm going to plot that on this data right here. It looks like 42 is probably going to be about here. So here's my mean. It says the standard deviation of the study time is approximately 8.77. So if I'm looking at this graph here, I called that 42. 42 plus 8 gets us very close to 50, so probably halfway between right here. 42 minus 8 is 34, so that gets me right here. So what I'm saying right here is that most of my data lies plus 8.7 above and minus 8.7 below. So we're looking at that, and that looks pretty true. We have 2 outliers out of 10, and the standard deviation, plus or minus 1 standard deviation, should represent about 70% of your data. So if I have 10 data points and 8 of them are represented in these standard deviations, then that's a good and true standard deviation. So what we can say here is, on average, the amount of time studying varies approximately 8.77 hours above or below (42). Or the average student spends between 33.3 to 50.7 hours studying. So that's most of the students spend between 33.3 and 50.7. Considering the following dot plots, would the standard deviation be less than or greater than 8.7? So what I'm saying is from that mean or that value of 42, so let's kind of draw a line right here of where I think 42 is going to be about. We're saying, does that standard deviation of 8.7, so plus or minus 9, does that grab about 70% of the data or most of the data? If I'm looking at this guy right here, this is that time studying. So there's that plus or minus. So this is yes, standard deviation equals 8.7. That's the very first example we are given. If I look at this next guy, that standard deviation of 8.7, yes, it grabs some of the data, but I'm still missing. It looks about 40% of the data. So I'm going to say my standard deviation is greater than 8.7 because I would need to make that reach a little bit longer on either side of the mean to get most of that data. On data set B, if I'm going from 42, I don't even need a standard deviation as large as 8.7 to grab most of my data points because they're stacked pretty closely. There's not a lot of variance. So I'm actually going to say here that my standard deviation is less than 8.7 because I can draw some pretty tight-knit circles, or I can see that most of my data lies very close to my mean in this situation. My very last data set, if I go that plus or minus 8.7, I'm looking right here, and it looks to me like I'm getting most of my data, but there are a few outliers, so I'm going to say it's going to be very close to, but maybe a little more. All right, so now that we know what this looks like with my strange, funky little drawings, let's see what this actually looks like when we look at distribution curves. You guys probably learned about some of these distribution curves before we went on break, hopefully. So normally we see three different things. We see our normal distribution, and we'll go over what that means in a second. We see our skewed right, or sorry, this is skewed left. And then we see our skewed right. So our median, since our median is always our middle number, remember that the median is always going to be exactly in the center of that block. So that's always the median or that middle value. But when you have some sort of skew, that means we have outliers that are pulling the mean away. So in normal distribution, the mean is also right there. So mean equals median. When it's skewed left, what that means is that you have an outlier somewhere to the left or a very low value that's taking that mean and pulling it away to the left of the median. So the mean value is less than the median. And when you have data that is skewed right, that means that we have an outlier somewhere to the right that's taking my mean to the right of the median, or mean is going to be greater than the middle value of those numbers. So this very first guy right here says, would you describe the life of a battery as approximately symmetric or skewed, and explain your answer? Well, if I look at this graph right here, I see that this mainly, it's not going to be beautiful and perfect, but it mainly looks like a pretty even hump. So I'm going to say that this is approximately symmetric because there aren't truly any outliers. and it looks to be about the same data to the right and to the left. Is the mean of the battery life closer to 95, 105, or 115, and explain? So you know that in symmetric data, the mean is going to be pretty close to the center of that bulk. So it looks like the center of that bulk is going to be about 105. Symmetric means the mean is at the center. Is 5, 10, or 25 a better estimate of the standard deviation? So now on these little blocks right here, I'm looking for about how much describes 70% of that data. So 70% of that data is going to be pretty much that highest little hump of what's going on right there. So if I'm looking at this guy, I want to know how far is it to get to the bulk of my data. So the bulk of my data seems to be, if my center value is at 105, it looks like we're going all the way to 115 to get to that top edge of the bulk, and then we're going down to about 90 to get to the bottom edge of the bulk of that data. 95, which means that it's probably going to be closest to about 10, because 105 plus or minus 10, or 95 to 115 describes most, or about 70% of my data. We have one more practice problem before you are good to go. Practice number 1 says the histogram below shows the distribution of the greatest drop in feet for 55 major roller coasters in the United States. Would you describe this distribution as approximately symmetric or skewed? I think we can all pretty much see this, but if I draw my hump right here, it looks like I have outliers far to the right. So what that's doing is my median is still going to be in the center, right? But that 410, 450, that little range right here is going to pull my mean away from the median. So we're going to be skewed right because outliers right of the median pull mean away from the center. Is the mean closer to 90, 135, or 240? Well, it looks like the median is going to be very close to 90. That's about the center of that hump. So since I have an outlier that's pulling it away, 240 is a little bit high. My mean's probably not going to be that large. That's not where most of my data is. So I'm going to say it's probably going to be closer to 135. And I say that because that's larger than 90, and it also looks to describe about the average. Is the standard deviation closer to 40, 70, or 100? So now that I have a value for the mean, let's get that on here. I said the value of my mean is probably going to be about 135, so I'm going to put the mean right here. So I need to see, like, how much does it take to get most of the data in? So from that 135, it looks like most of my data lies within this bulk right here, right? Because that looks like it describes about 70% of that value, or like most of that hump right there, most of the area under that curve. So according to that, if that's 135, it looks like I went all the way up to 210, and then I went down to about 50. So from 130 to 210, and then down to 50. It looks like it's going to be closest to 70 because about 70% of the data is 135 plus or minus 70.